Should I share the screen now?
Yes. Hello, good evening all. I welcome you all for this special seminars on the quantum entanglement. So this seminar has been organized under the theme of the SPS School of Physical Sciences Seminar 2022-2023. And we have a special session today where we will be talking about, or we'll be learning about the Nobel Prize in 2022 in Physical Sciences. So we have two seminars in the series. First will be by Professor P.C. Deshmukh and the second one will be by Dr. Manik Banik. So we put the event name as 2 hours of quantum entanglement. So we'll have like a complete understanding of the entanglement, which is a very unique phenomena in physics. So we'll start with the first talk by Professor P.C. Deshmukh. Professor P.C. Deshmukh is a theoretical atomic physicist who is currently mentoring and convening the Center of Atomic and Molecular and Optical Sciences and Technology in IIT Tirupati, and he is also adjunct professor at IISER Tirupati and the Department of Physics, Dayananda Sagar University, Bangalore. So he is associated with the different institute at this moment. He has previously worked as a professor and dean of sponsored and consultancy at IIT Tirupati. And he was also a professor and HOD, head of the department at IIT Madras Physics Department. And he was the professor and dean of academics at IIT Mandi when the IIT Mandi was in the inception. And Professor Deshmukh has more than 150 research publications in various journals. He has published 2 books on fundamentals, foundation of classical mechanics and quantum collisions in confinement of atomic and molecular species and photons. So there are a lot of students and of course the young faculty member have learning from him. And today we will learn about whether the reality is really non-local or local. So Professor Deshmukh, the dais is with you.
Okay, thank you very much, Ajay. Thank you very much for giving me this opportunity to be here at IIT Mandi. And before I begin, I would like to say that when Ajay asked me to talk on this occasion, I did not want to do it for 2 reasons. One is that I have talked on this very recently, and that talk is available on the YouTube already. And much of the content may be common. That was one reason. So I was very reluctant to accept this invitation. Second, I had the opportunity to hear Manik very recently when he gave a talk at IIT Tirupati, and it was a marvelous talk. And I thought that he's going to cover, he being a specialist in the area, he would cover all the aspects, and there may not be much for me to add. So having given you 2 reasons why I was reluctant to speak today, I should also give you the reason why I finally accepted to be here. And the reason, of course, is IIT Mandi. As Ajay said, I spent 2 years at IIT Mandi when the institute came up. This was in 2009, 2010. I was in deputation from IIT Madras. And I have considered IIT Mandi my home institute for a long time. So it's always such a pleasure to participate in any event organized by IIT Mandi. So here is a title which I challenge by asking, isn't asking this question a faux pas? Why is reality non-local? And this question is a faux pas. Faux pas is a blunder. And why is it a blunder to ask this question? And this is a point that I will discuss in today's talk. And let me begin by celebrating the fact that amongst the six intellectual giants you see on the screen, there is only one who did not get a Nobel Prize. And he's the one who is applauded for making the most profound discovery of science. But then everything begins with Einstein. Means so many things, including special theory of relativity, general theory of relativity, Brownian motion, and even quantum mechanics. Means a lot of people argue that it is not to Max Planck in 1899 that we owe the origins of quantum mechanics, but to Albert Einstein in 1905. And it was in fact for that work that he got the Nobel Prize. But then he continued to contribute both by developing quantum mechanics and also by questioning its foundations. So in both ways, he contributed in a big way. And the big question in front of us today is just what is reality? And this question was discussed. It was debated very hotly between Einstein and Bohr. This is the most famous picture which each one of you, I'm sure, has seen and perhaps has it with you on your laptops. And this question was discussed at the Solvay conference in 1927. And everybody, by 1927, Schrödinger had already developed perturbation theory, and many successful applications of quantum mechanics were seen by then in spectroscopy. And then in 1928, Dirac developed relativistic quantum mechanics. All these developments were taking place. But then there was something, mysterious about quantum mechanics. And that is something which was bothering many intellectual giants, including Einstein. There were others too. Because the very notion of reality was implicitly challenged by the quantum theory. And how exactly it was challenged really depends on what we meant by reality in the first place. So, the general understanding of reality is based on the classical question in mechanics. We ask, how do you describe the state of a system and how does it evolve with time? If we get a consistent answer for this, and if we can actually account for mechanical motion of all objects by having some universal law which answers these questions in a simple manner, and that becomes applicable to all the dynamics that we see, then we would say that we could say that yes, we have some perception of reality because it answers this question in a nice manner. And this was answered in terms of describing a mechanical state by a point in the phase space, the position and velocity, or equivalently position and momentum in the Lagrangian or Hamiltonian formulation. And if we describe a system fully by this, and in fact this point in the phase space indeed describes it fully, and how it evolves with time is explained by the equations of motion. And these equations of motion can be either the Galileo-Newton equation of motion, or it can be the Lagrange's equation of motion, or the Hamilton's equations of motion. They're all completely equivalent to each other. But they tell you how the position changes with time, dq by dt, or how the momentum changes with time, dp by dt. And if you can have a consistent answer for this, then it develops in your mind a certain notion of reality, because it answers how you describe the state of a system and how it evolves with time. This is our understanding of reality. And there is a good reason why we associate reality with this understanding, because we can relate to position, velocity, momentum, all of these things seem to be very real in the sense of our usual vocabulary. And there is a good reason for this, because it describes large number of phenomena in our daily experiences. For example, it explains the planetary motion. It explains to such an extent that Neptune and Pluto could actually be predicted from these equations of motion. And they were eventually discovered. They were predicted to be in a certain point in the solar system, and they could actually be discovered by training telescopes in that direction. So there is a good reason why reality is associated with this. I just gave an example from astronomy, but there are examples in our day-to-day experience all the time. Now, this is challenged in quantum mechanics, and this challenge came over 100 years ago, about 100 years ago, within the 10, 15, 20 years around that time. And it came in the works of de Broglie, Schrödinger, Heisenberg, Born, Jordan, Einstein, Satyendranath Bose, von Neumann, Dirac. Many contributed to this. And their works demanded a reality check. The reason to demand it, because the entire scheme of classical physics is based on this idea that you solve the differential equations, Hamilton's equations or Lagrange's equation or Newton's equation. And these are differential equations. You integrate the differential equation to solve them, and you require constant of integration to get the complete solution. And if you look at Hamilton's equations, there are two first order equations, and you need two constants of integration. If you look at Newton's equation, it's a second order equation, and you still need two constants of integration. And these are the initial position and the initial velocity, or the initial position and the initial momentum, depending on which scheme you're implementing. Now, it is taken for granted that this is knowable in the first place. And if it is knowable, no problem, you can go ahead and solve the differential equations. But then, are they knowable at all? And you need simultaneous information about both position and momentum to be able to use Hamilton's equations or Lagrange's or Newton's or whatever. And can you actually determine both of them together? And in a paper in 1927, Heisenberg explained the idea using a thought experiment, a Gedanken experiment that is now referred to as the Heisenberg microscope experiment. And let's say you're looking at a particle and you look at it by shining light on it. And we know that light carries momentum. This is the momentum that we meet in the Poynting vector. We meet this in the tail of the comets. And this momentum would dislodge the electron in a certain way, and the scattered photon will be seen through the eyepiece of the Heisenberg microscope. And if you just do a very simple optics assessment of this using the focal length and resolving power of the microscope, then you know that if the photon is scattered in the same direction in which it was originally moving, which is along this line, or in the opposite direction, which is along this line, I hope you can see the cursor, then there is a certain range of momentum transfer. And the accuracy with which you can measure the position and momentum is compromised in this process. And the Heisenberg microscope argument from optics gives you this product to be about twice the Planck's constant. Actually, the uncertainty, this is just a model demonstration. The actual uncertainty principle requires quantum mechanics, not just optics. You need quantum mechanics because we discover that simultaneous information about position and momentum is not possible. And that is something which the Heisenberg microscope illustrates. And if it is not possible, then classical physics collapses because it requires position and momentum together to solve the classical equations of motion. And if the scheme collapses, what do? You need a new scheme. And this new scheme was quantum mechanics. And this new scheme seemed very abstract, that, okay, you do not represent the state of a system by a point in the phase space, but you represent it by a vector in the Hilbert space, and dynamical variables are operators, and then you developed the operator algebra. And then by processing this algebra, you get information about physical properties of the system. So this appears to be very strange, but it works. Nothing succeeds like success. And in as much as classical physics we saw is internally inconsistent, it is based on simultaneous knowledge of position and momentum, which are not knowable. Quantum mechanics gives you a consistent theory of nature. And it gives you a consistent theory of nature to which you have not been able to find any exception. But then there is a price to pay. And the price is that quantum mechanics intrinsically brings in uncertainties, probabilities, and statistics. Now, you have to analyze this in terms of expectation values, state vectors, and there is a complete new algebra which is required. And I will put my finger on one particular aspect of that algebra, which is the interpretation of probability. That if you express the state vector as a linear superposition of some basis set, then the modulus square of the coefficient gives you the probability that the system is in the particular base vector state, which is in this case the ith component. Now we are going to discuss this relation extensively in this lecture. What it leads you to is something very spooky. And as Feynman says in one of his lectures, that all the mind-boggling spookiness of quantum mechanics is contained in the Young's double slit experiment. And I assume that all of you are familiar with the Young's double slit experiment. You might have even performed this Young's double slit experiment. And the strange thing about it is that if you have only one slit open, then you get one intensity profile. If you have the other slit open, you get the other intensity profile. And if you have both the slits open, you get dark and bright fringes. And in the first course in quantum mechanics, all of you would have sorted out this matter. Now, this is really spooky. And I want to spend some time discussing the spookiness that comes out of the Young's double slit experiment, because it becomes spookier and spookier. So here are the fringes in a Young's double slit experiment. And it doesn't tell you from which slit the particle, whether it is an electron or a photon, it doesn't matter. I would refer to it as a Feynman particle because it is very neatly One can analyze it using Feynman's path integrals. So whatever it is, you decide to spy on it because the experiment is not telling you whether it went from one slit or the other slit. And it is therefore tempting to spy on this experiment and find out from which slit it would have come. So you perform what is called as a which way detection. And what happens is that if you do a which way detection, the fringes that you had seen earlier, they disappear. Now, this is very strange. Now, what makes it even stranger is that if you now install a lens which combines these rays so that you lose information at your eyepiece, whether the ray has come from here or here, because they would have converged to the focus here, you have lost the information which was obtained from the which way detection. And what the which way eraser does, this erases the which way detection part and it restores the fringes. It restores the interference. Now, this is very strange. By putting a lens here, the particle has to be explained in terms of a superposition state which includes the slit 1 path as well as the slit 2 path. And just by installing this lens over here, this analysis must change, because if you don't install it, you have the which way detection and then the fringes are lost. Now this is spooky. Now it gets spookier, because if you now put this lens far away, and this is what is called as a delayed choice experiment, you put this lens, notice that it can be placed very far outside what we perceive as the physical apparatus. It can be way outside, even kilometers beyond it. But if it is there, and if it has the capacity to merge these tools into a focus point, then it works as an eraser and the fringes are restored. So this is even spookier. Now let's carry this further. This is what I will call as spookiest. Here is a Young's double slit experiment, and I have a slit 1 over here and a slit 2 over here, but there is another shutter over here and there are additional slits over here. And as you can see, there are alternative ways in which light can be scattered from the slits and can also get scattered by these stray objects, one over here and another over here, and then go through this cyclic loop. And all of these generate a complex amplitude, because the wave function must be described as a complex function. You cannot do quantum mechanics by two real vector spaces. You need a complex vector space. And these are complex amplitudes which must all be added. And then after completing the addition, you take the modulus square to get the probability. This is really spookiest, because look at the paths. They are mind-boggling. And then we come to what I may call as spookiest test, something beyond spookiest. Because where are these scatterers? You can place them anywhere. They can be on Mars, they can be in the Andromeda galaxy, wherever, which is like 2.5 million light years away. And this whole apparatus is in your laboratory, okay, over a span of maybe 1 or 2 meters. And then you start worrying about how much time light would take, which travels at a finite speed, to go to the Andromeda galaxy, bounce back, and then enter the apparatus to generate a meaningful complex amplitude, which should also be taken into account. So you have to sum over all the histories. This is really mind-boggling because you are asking how much time would it take. But then if you ask this question, you're forgetting that you're talking about a path. And if you know the position, you do not know the momentum, you do not know the speeds. And these two are not knowable to begin with. So that's not even the right question to be asked. And Niels Bohr explained this once by saying that quantum mechanics does not answer all the questions, but it tells you what are the right questions to be asked. And it would begin to give you some clue about why I said that the title of this talk, Why is Reality Non-Local, is a faux pas. We will see it further because we will discover that that's not even the right question to be asked. So we have seen that the which way marker destroys the interference, and we understand it from quantum mechanics very neatly. Because the moment you have marker states, and these marker states are orthogonal to each other, which is why they are marker states at all. And it is this orthogonality of the marker states which destroys the interference. So that explains how the spookiness, the spookier experiment, and the spookiest interpretation of the Young's double slit experiment is understood in terms of quantum probabilities, which are the modulus square of these coefficients. These are the Born probabilities. They are not born out of the Born interpretation. They are born out of nature. And they are interpreted in terms of the Max Born probabilities. And they are given by the modulus square of these coefficients. So this is a key point which is going to play a significant role in our discussion. So having accepted that probability is an integral part of quantum theory, we now ask, where is the uncertainty coming from? Because uncertainty and using probability theory, using statistics is not alien to physics at all. Okay, there is a chance when you toss a coin, you may get heads or tail. All right, right from the time of Mahabharata, or if you go to a casino and spin a wheel, you don't know where it is going to stop. And if you're lucky, you win the jackpot. Otherwise, you can even lose your money. So there is an element of chance in classical physics. But where does this chance come from? Suppose you know when you're spinning this wheel and you know exactly how much torque you have applied and you know exactly how much friction is there and you know all the geometry, the mass, and all the parameters. Can you not actually work out a calculation and predict as to where the wheel would stop? You certainly can. And the reason you are not able to win when you spin the wheel, or you're not able to win the toss in a cricket match, the captain is not always able to win the toss because he doesn't know how much force he has applied on the coin. What are the other variables which are involved in the dynamics of the spin of the coin? What kind of air is it spinning through? Is it humid? Is it dense? Is there pollution in it? And all this is going to determine how it will finally land and whether it would land reverse or obverse, heads or tail, or where the coin that you spin, the wheel that you spin, where will it stop? So this uncertainty, this lack of information, these are the hidden variables in the theory. If you knew all of them, you could actually predict where the spinning wheel would stop, and you would always win. And it is this hidden variables which go into the classical probability theory in statistical mechanics, in Maxwell-Boltzmann distribution, and you work with probability formalism because there are hidden variables. And it is therefore meaningful to ask that, okay, now you have uncertainty in quantum mechanics, and a system is in a state of superposition of all its eigenstates in a complete basis, and the probability that it is in one of them is given by the modulus square of the corresponding coefficient. And when you perform a measurement, the system collapses into that state. But the probability is given by the modulus square. So there is an uncertainty. Is it coming from some hidden variables? Just as it does in classical physics. So this is a very relevant question which Einstein raised. And in fact, he argued that there is something missing in quantum mechanics, which is this information. And if only this information is plugged back, if some future studies reveal this information, then you could recover probabilities as per classical physics. So something is missing in quantum mechanics. And Einstein based his argument on some thought experiments. These were debated at the Solvay conference in 1927, but the discussions and the debates continued. And this is a paper, the famous EPR paper, the Einstein-Podolsky-Rosen paradox, as it is referred to. And I will only illustrate the essence of this paradox. The essence of the paradox is here, that if you have a singlet state or any fission that takes place, okay, and there are these two particles which fly away from the fission point in opposite directions, then just to make the argument simple, if position and momentum of this particle is not knowable simultaneously, and we accept quantum theory, position and momentum is also knowable, not knowable simultaneously for this. But what if we measure the position of this particle and measure the momentum of the other one? If you measure the position of one particle and measure the momentum of the other particle, then from symmetry and conservation laws, you can get position and momentum of both the particles. And that would be in conflict with quantum theory, so that sounds like a paradox. And despite this argument, if you still cannot get simultaneous information about position and momentum, then there must be some hidden variables in the which a future theory would reveal. That was the argument. And this was again contested by Bohr. And here, notice that you are estimating the momentum of this particle using conservation principle, but you are measuring only the position of this particle. And you are assuming that momentum of the other particle, momentum of this particle, the blue particle, is a meaningful property to talk about even if you do not measure it. And this is straight from Einstein's paper. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. So it assumes that even if you don't measure momentum, it is a part of your reality. And you may look for indirect ways of getting that information. So these theories are called counterfactual definiteness theories. That even if you do not measure a property, it is meaningful to talk about it, and it becomes an integral part of the reality that you are considering. So this is the notion of reality, and Einstein defined it very categorically. And this was in the context of reality as it was understood at the time of this debate in the 1920s and the 1930s. But then it was not easy to figure out what exactly is the nature of reality. It was not possible to find out if quantum theory belonged to the class of theories which are which satisfy counterfactual definiteness. And Bohr replied to Einstein's paper in a follow-up volume in the same year, and he argued that Einstein's arguments, whatever conclusion they led to, were not appropriate. There were fallacies. And this was in the same spirit of the Bohr-Einstein debate at the Solvay conference. So here is the thing that um, here Einstein maintained that future theories could eliminate quantum uncertainties if they could explain the lack of information which belonged to the family of hidden variables. And it took quite some time to figure out. It took 3 decades from this debate. And John Bell in 1964, he pointed out, he came up with a method to analyze the subtle aspects of this debate. Means Bohr argued against Einstein. He won those arguments, and he could show that Einstein's arguments were fallacious. But he did not have a rigorous way of demonstrating that the probability in quantum mechanics is intrinsically of a different kind. That is a different question. And that could be answered only in the works of John Bell 3 decades later. And let us try to understand this in the light of these uncertainties. So we considered this uncertainty: when you toss a coin, you may get a heads or tail. And if only you predict, you could have information about all the hidden variables, you could actually win the toss every time. And the reason you are not able to do it is because of the hidden variables. So John Bell figured out that if correlations in this probability can be studied, not just one toss at a time, but if you look at a toss in which Dhoni is involved, another in which Smriti Mandhana is involved, and the third in which Rohit Sharma is involved, and each of them would get either a head or a tail, and then examine if what are the correlations. Dhoni gets a head and Rohit Sharma gets a tail. Rohit Sharma gets a tail. Smriti Mandhana gets a head. So there are, 2 states for the coin to land in. And you examine these and look at the correlations between these events. Then you can come up with a criterion to determine if the probabilities are governed by hidden variables or they are not. If that theory belongs to the scheme of counterfactual definite theories or not. So that is the resolution which John Bell provided. So let us look at these three experiments, and I will label them as red, green, and blue for these three events. Okay? So let us consider three events: the red, the green, and the blue. And let us consider three circles: the red circle, the green circle, and the blue circle. And now you notice that in as much as the coin could land in either head or tail, there were two states. Each of these circles is double valued in two different ways. The red may overlap with green, or it may not overlap with green. The red may overlap with blue, or it may not overlap with the blue. And this is true for the other circles as well. So each is double valued in two ways. And now you go ahead and number these sections. So there are these 7 sections. And now you play a game that you played in your childhood, which is to pin the nose of a cartoon. Okay, there is some picture. You're blindfolded. You're not able to see anything. You're completely blindfolded. And you're given a pointer and asked, or a pin, which you place directly on the nose of this picture. And what you're going to do is you may end up pinning it on the nose, or maybe somewhere else on the face, or maybe on the ear, or wherever. Okay? And you play that game with these 3 circles. And ask yourself, what is the probability that you have hit the region 1? What is the probability that you have hit the region 4? What is the probability that you have hit the region 5? And you can immediately see that there is an inequality. That 1 plus 4 plus 2 plus 3 is greater than or equal to 1 plus 2. And these portions are green, not blue, plus blue, not red, is greater than or equal to green, not red. And there is an inequality that you run into. What is interesting about this inequality and how it brings us to the Bell's inequality is this: that when you look at green, not blue, there is a third, red, which you have not talked about. It is a hidden variable. It includes yes red and no red. So green, not blue, red, and green, not blue, not red. So there is some additional information which is locally available but not explored. And you're assuming in your counterfactual definite argument that this information is there. In principle, you can extract it, although you have it, but it is available, and the same inequality can be written by including G naught blue. In G naught blue, you include both of these terms, and you do the same with the other ones, and you get this inequality. And this involves the local hidden variables in a counterfactual definite theory. So in a counterfactual definite theory, if you have probabilities which are knowable in terms of local parameters, then this inequality should be satisfied. The actual argument is much more complex, but this is the essence of the argument. That any theory which is based on locality and local hidden variables, if it belongs to the family of counterfactual definite theory, then a certain inequality must be satisfied. You can frame this inequality in a number of different ways. These are the Bell inequalities. And what John Bell proposed is that you can test this inequality because these are required by local hidden variables in a counterfactual definite theory. So if Einstein's argument was correct, then this inequality would be maintained. And now, 3 decades after the debate between Bohr and Einstein, you finally had a way of checking whether the probabilities, the uncertainties, were due to local hidden variables in a counterfactual definite theory. So that was the great contribution of John Bell in this paper in 1964, which was on the Einstein-Podolsky-Rosen paradox. And you can actually do an experiment to test it. And here is an experiment that you can test. You can have a singlet pair of spin half particles, and if they fly away in a fission and detected by Alice and Bob on opposite sides, then you know that if one gets spin up, the other will get spin down, and vice versa. And we talked about these 3 experiments, the red, the green, and the blue. Okay, the Dhoni's experiments, Smriti Mandana's, and Rohit Sharma's, right? The red, green, and blue. You can do this analysis in quantum mechanics using any base pair. And you can carry out these measurements because your base pair for spin up and down means what is up and what is down. Means up is just the direction of the Z axis of the magnetic field. And you can have a basis set consisting of up and down in any orientation. You can use this, or you can turn it around, or you can rotate it in any which way, and you still have a valid basis which are mathematically completely equivalent to each other. So you consider 3 alternative basis sets which are rotated with reference to each other, and this experiment is very similar to the toss. Again, there are 2 possibilities because you may get a spin up or a spin down, and you do this experiment with alternate. You carry out these measurements. Alice and Bob carry out these measurements using alternate base pairs. They are basis sets in which the z-axis, the magnetic field, if you are carrying out this detection in a Stern-Gulrack type experiment, then these magnetic fields, the base pairs can be oriented in different directions at 45 degrees with the first, or 90 degrees with the other, and so on. And you can carry out these 3 different measurements which correspond to the red, the green, and the blue. And now you can ask, would local hidden variables make quantum theory complete? This was the basic question which Einstein was raising. And here, if local hidden variables were to make quantum theory complete, then you would expect an inequality of this kind to be satisfied, which is the Bell's inequality, which must be satisfied in counterfactual theories in which local hidden variables play a role. However, quantum mechanical probabilities are coming from this consideration. And I had alerted earlier that this equation is going to play an important role in our discussion. It's a very simple one that you met in your first course in quantum mechanics. But here, the probabilities are determined by these coefficients and not by hidden variables. And you can use this expression. You can do the quantum mechanics using this expression of the Born interpretation of the wave function. And then you can ask that you have these 3 orientations, the green, the blue, and the red. And then you ask for these correlations, that what is the probability that Alice gets up and Bob also gets up when his experiment is at 45 degrees with respect to Alice's, and they don't know what is the orientation being used by the other. And then if you do a simple analysis based on your usual Born interpretation of quantum mechanics, you would expect an inequality between the correlations to be according to Bell's inequality. But what you find when you use this consideration, you have to work with these coefficients, these modulus coefficients. Those are the ones which determine the probabilities. And they involve the sine and the cosine of the difference angles. They do not involve any hidden variables. They are based on the sine and the cosine of the difference angles. So this analysis is not very difficult. One can carry out. And then when you put in these numbers, the 45 degrees, the sine of the corresponding angles, and the cosine of the different angles, you actually find that the Bell inequality is violated. And you are led to the conclusion that quantum mechanical probabilities cannot arise from hidden variables, which are there, but you haven't seen. But you believe they are there. That is your notion of reality. You believe that these hidden variables are there even if you do not measure them. It's like predicting that there is a momentum of a particle even if you do not measure it. So this is the counterfactual definiteness which was there. And essentially, the Bell inequality must be satisfied by all theories which are both local and counterfactual, but they are violated in quantum mechanics experiments. Which means that hidden variables, local hidden variables, and counterfactual definiteness cannot account for the uncertainties in quantum mechanics. And it is for this reason that Bell's work is celebrated as the most profound discovery of science. And in fact, there is a story that Niels Bohr, who was 75 years old, and Bell was a young man in 1960, they met at CERN in an elevator. And although Bohr's intuitive arguments against Einstein's were successful in showing that Einstein's argument was not correct, Bohr had not come up with a rigorous mathematical way of demonstrating as to how exactly this should be tested. And the Bell's inequality really gives you a mathematical test. And these experiments were performed first by Clauser. In fact, Clauser, Horn, Shimony, and Holt in an inequality. They tested an inequality which is called as CHSH inequality, which belongs to the same family of Bell inequalities. Clauser did these experiments with a graduate student, Stuart Friedman. They looked at the cascade transitions in atomic calcium from the 4p2 state to 4s4p and then to 4s2, and then looked at the polarization states, and they found that the Bell's inequalities were violated, but then there were some loopholes. And what it turned out that certain counterfactual and local theory could also reproduce the data, and then a loophole-free test was carried out by Alan Aspect, Zeilinger, and these three are credited with the experiments which show that Bell's inequalities are actually violated. So we arrive at an important conclusion and an important understanding of quantum mechanics, of the probability in quantum mechanics. And new technologies are emerging. This is what everybody refers to as the second quantum revolution. The quantum mechanics last century already gave us new technologies, semiconductors, lasers, whatnot. But now we are being led to cybersecurity, quantum networks, many other technologies will come, and perhaps Manik will talk more about this. But what is at the heart of this is the transition from how you do computing using Boolean algebra, the bits, the 0 and 1, and you use classical gates, the AND gate, the NAND gate, the OR gate, and so on. But now, what you get from the Young's double slit experiment is a superposition of 0 and 1. So that's the qubit. And when you do mathematics, when you do computing with qubits, you are led to completely mind-boggling technologies, which is the second quantum revolution. And some of the early works are due to David Deutsch, Peter Shor, Love Kumar Grover, and so on. But these technologies are based on one essential idea, which is entanglement, which comes from the principle of superposition. And this entanglement enables teleportation. So these are the fundamental ideas which enable these new technologies and the second quantum revolution. So what is this entanglement and teleportation? So first we know what it is not, but then we ask what it is. So you have a qubit, which is a superposition of a dead cat and a live cat. And you have another qubit, which is also a superposition of a dead cat and a live cat. And now Alice and Bob are replaced by Alka and Bablu. And these are distinguishable qubits, which itself is a mystery. Because the wave function of any object spreads all the way to infinity. So distinguishability itself is a mind-boggling idea. But you consider distinguishable qubits, and notwithstanding the fact that the radial functions go to zero of bound states only in the asymptotic region as r goes to infinity, but then these qubits, when they are entangled, what it means is that you cannot write the quantum state of the two qubits as a tensor product of two single qubits. So this is the defining relationship of an entangled state. This is what is called as a Bell state, and between two qubits you can have four different types of Bell states. And if you look at these expressions, notice that you cannot predict if the qubit 1, if Alice's qubit, you can distinguish between them. You know which is Alice's and which is Bob's. There is no confusion about it. You cannot predict whether Alice's is in state 0 or 1. But whichever is Alice's state, Bob's would be the same if the Bell state is one of these. And the same thing you can predict from here. Here you know that it will have to be the opposite to Alice's. So this is the characteristic signature of a Bell state. These are entangled. The probability that Alice has one or the other is only 50%. But once you know that, then it is guaranteed as to what Bob's state is. And this has nothing to do with the distance between the two qubits. The two dead cats or live cats, which you see in this picture, they can be close to each other. They can be in adjacent rooms, in adjacent labs, in adjacent countries, or in adjacent galaxies, wherever. The distance is not a factor of reckoning at all. Regardless of where the qubits are, the entanglement survives as long as a measurement is done, which is when the system collapses into an eigenstate. And what enables this technology is this entanglement. Because of this entanglement, you can understand this entanglement in terms of teleportation, that if Alice has a quantum state of superposition of 0 and 1, and she wants to communicate this information to Bob or Bablu, who is at a significant distance or wherever in the universe, they make use of additional resources. They have two other qubits, and these two qubits are in a state of entanglement. So their state cannot be written as a tensor product of these two vectors. And there are What Alka or Alice can do is to entangle this qubit with this, which will influence this qubit in a manner which depends on the state of this superposition. And that is how Alice can send information, quantum information, to Bob at a remote location. Now, there is still a question to be answered, because Bob will not be able to get this, extract this information, unless Alice tells him how she has entangled this with this, because there are 4 different possible Bell states between these 2 qubits. And she must communicate this information using conventional communication channels. These are the classical communication channels. And they, of course, will not exceed the speed of light. So no question that special theory of relativity is compromised. But there is a bigger reason why special theory of relativity is not compromised, regardless of the distance between these 2 qubits. Because from the very beginning, the distance between the 2 qubits was not a factor at all. That what we call as here and there is not a factor at all. It is not some information which is going from here to there. When you talk about anything traveling either at a speed less than the speed of light, or at the speed of light, or faster than the speed of light, you're talking about something going from here to there and from time t1 to time t2. Here, there is neither a difference between t1 and t2, it is at an instant, nor is there any difference between here and there, because it is the collapse of locality. The local hidden variables we have seen do not account for the probabilities which are measured in experiments. So reality itself turns out to be non-local. And there is no question about violation of any speed limits. So there is nothing like superluminal speed, and what we find is that the point raised by Einstein is pretty much resolved by this entanglement, which is what generates new technologies. So the big point is that yes, it is spooky. It is very spooky. But the spookiness has nothing to do with anything going faster than the speed of light. On the contrary, it has to do with the fact that our notion of reality in terms of local space must be refined. This is what we must interpret as the new reality. I call it as reality 2.0, because it destroys the difference between here and there. So now let's go back to the question. And I mentioned that we have a title for the talk, but it is a faux pas. And I want to answer it by, toward the end of this talk, by pointing out, by raising another question in which we ask a similar question. We ask that you have got a circuit over here. Okay, this is electrical circuit, but there is no source of electricity here. You just have a magnetic field, and you move this wire from left to right or right to left. Okay, and when you move this wire, we know that a current flows because the wire is in a magnetic field, and this current can be detected in an ammeter. And we can ask, why does a current flow? And undergraduate physics answers it. You can ask another question, that you have another experiment in which you're not moving the wire, but you move the magnetic field. And then again, you see that there is a current that flows. And you can ask, why does the current flow? But the answers are different. In the experiment on the left, you are using Lorentz force law. On the experiment on the right, you're using the Faraday-Lenz law. The answers are different. And this is really stunning. In fact, Feynman points out in Feynman lectures that there is no other place in physics where such a simple and accurate general principle requires for its real understanding an analysis in terms of two different phenomena. You can't dismiss it as a trivial thing that, okay, what is a big deal? It is motion is just relative. Sorry, it's not that. That is a Galilean relativity that you're talking about, which does not explain this. What you need is the special theory of relativity. It comes from the fact that the speed of light is constant in every inertial frame of reference. And the only way you can account for this, and this is what led Einstein to the special theory of relativity. In fact, Maxwell's equations led him to that. When you take the curl of the curl equations, you get the wave equation in which the constant speed of light pops out. And Einstein was bold enough to conclude that the speed of light is constant in every inertial frame of reference. You don't answer why is it so. You only describe it. That this is how you describe it, which gives you the correct interpretation of the laws of nature in the experiments that you perform. You perform the Faraday-Lenz experiment, you can understand it fully in terms of the special theory of relativity. You reformulate Maxwell's equations in a Lorentz covariant fashion. Everything comes out very nicely. And you can attribute it to the constancy of the speed of light in all inertial frames of reference. But would you ask, why is the speed of light constant in every inertial frame? You can't do that. Because all questions finally, if you ask the why type of question, you end up at a dead end. You cannot take it further. And the correct equation that ought to be asked is, what is the law of nature? And not, why is the law of nature what it is? So here in quantum mechanics, we find that quantum theory is either non-counterfactual or non-local. And this is the new meaning of reality, which I call as reality 2.0. So that explains why I called this title as a faux pas. You do not ask the why. What is the right question and not why? And now I need your help in having a new title for this talk. I will propose two alternatives. You can pick whichever you like. One is, what is the nature of reality? And the second is, what is the reality of nature? Thank you very much.
Thank you very much, Professor Physics. Yeah, thank you very much for, now I can say really a good talk. And it also raises a question, I mean, like the understanding what we have for the reality is driven by the hidden parameter. So is reality really real or something else? Okay. So with that, I open the session for the questions. If anybody has a question, please, you can raise. Anybody from the student side? Because sir has asked the question, so either you have to answer it or you ask the question. Anybody from online? Hello? Come on, ask the question. Yeah, please.
Sir, in the
Manju, you can take this mic here. There is a student student, PhD student Himanshu is asking the question.
Yes.
Okay, sir, in the spookier experiment where you double slit experiment,
Mhm.
so when you said that the optics which we are seeing it, the optics is far from the experiment, and then
Yeah.
we are getting the
Yes.
so so can we in that experiment can we determine that from where the electron is coming?
See, if you do a which way experiment, a which way experiment is the only experiment which will tell you from which slit the particle has emerged.
Okay, sir.
If you erase that information, it is like destroying the which way information. And when you destroy that information, the fringes reappear. That is the essence. And it has nothing to do with where the which way eraser is placed.
Okay, sir.
Because because the parameter of distance never entered our discussion. The very presence of the marker states expands the Hilbert space. And you get the orthogonality in the two states, M1 and M2, which I had labeled, if you remember that. Those are orthogonal, and that orthogonality destroys the interference pattern. But you have an eraser which destroys that information, which restores the interference. Now, this is the spookiness of quantum mechanics. And Einstein had every reason to worry about it. Yes.
In that way, I was thinking, in that way, like every double slit experiment, whenever we are doing double slit experiment, there will be one like this kind of. Okay, yeah. No, I have no question.
Okay. This was the question he understood very well. So, any other question from any?
So I have a question.
Yeah.
Yes.
So maybe you can introduce yourself and then you can ask the question.
I'm a PhD student. My name is Lavak.
Yes.
Uh, in the bell test experiments, you are saying there are loopholes. There are much more better experiments,
Mm-hmm.
and the one suggested, like in the example you have given. So,
Yeah.
what kind of loopholes are there? Like, what do you
Well,
mean?
uh, that is a subtle question, and one really has to get into the details of the experiment, which I have bypassed completely. The loophole was that it was possible for a counterfactual theory based on local hidden variables which could also reproduce that result. And that was the loophole. But then the subsequent experiments by Allen Aspect and Zeilinger, these loopholes were totally removed. But it doesn't mean that Clauser experiment was wrong or misleading or anything. On the contrary, it was the first demonstration of the fact that Bell's inequalities are violated in physics experiments. So nothing wrong with it, which is part of the reason that Clauser, Aspect, and Zeilinger, all three of them get a Nobel Prize. John Bell is the only one who missed out on the Nobel Prize because sadly he died rather young before the experimental verification came out. Otherwise, he certainly would have got a Nobel Prize as well. So those are the loopholes, and there are very complex discussions on these loopholes. Maybe I think it is time for Manik to take over, and he might talk a little bit about some of these loopholes.
Yeah, can I add?
Thank you. So, thank you, Professor PCD, for the interesting talk. Let's thank the professor one more time.
Thank you very much. I'm really grateful to you, all of you, for the opportunity for patient hearing, and I'm looking forward to Manik's talk now. Thank you.
Thank you, sir. Yeah. So with that, we move on to the next seminar by Dr. Manik.
Yes, yes. Can you hear me?
So, yeah, let me just introduce you, and then Meanwhile you can share your screen.
Am I audible now?
Yes, you are audible. Well, so Dr. Manik Banik is associate professor in Department of Physics at Bose Center for Basic Sciences, and he did his graduation in science and post graduation in physics from Jadavpur University. He started his research career at Indian Cellular Institute, Kolkata, and received his PhD degree by Kolkata University. He worked as a postdoctoral fellow at Institute of Mathematical Sciences, Chennai, and his primary research includes foundation of quantum mechanics, quantum information theory, quantum thermodynamics, quantum communication theory, and causality in quantum world. And Dr. Banik has published 15 research articles in international journals, and he's going to talk about the Bell's theorem and the current research what he is doing. So we'll have like an additional of the knowledge what we have so far. The dais is with you, Dr. Banik.
Yeah.
So
Thanks, Professor Soni, for this nice introduction.
we are not able to see your screen. Just a minute. Yeah.
Yeah. Can you see my screen?
Yes. Now we can see.
Yeah. Yeah. Thanks for this introduction, and I'd like to thank you all to invite me to talk about this. So there will be a huge overlap what I'm going to talk and what Professor Deshmukh has already talked. But I think it is not a very bad idea to repeat this discussion because these ideas of Bell non-locality is not that much popular among physicist community. So today I have choose the title of my talk is Bell's theorem, the most profound discovery of science. This talk actually I have presented in IIT Tirupati very recently. So as all of us know, and Professor Deshmukh in his talk mentioned, these three professors has received the Nobel Prize this year, Alan Aspect, John Closure, and Anton Zeilinger. And Nobel Committee mentioned in their side that this for experiment with entanglement photons, establishing the violation of Bell inequalities and pioneering quantum information science, the Nobel was given to these three people. So my main motive was in this talk will be to understand what does Bell inequality violation implies, to understand that precisely. So I'll take a motivation from this quote. One is by we know only one by Karl Marx, that we know only one single science, the science of history, and then Imre Lakatos, that history of science without philosophy of science is blind, and philosophy of science without history of science is empty. So I'll take a historical perspective to understand the philosophy underlying Bell's inequality derivation. So as we know, the methodology of scientific research program is actually fundamental three-step process: thesis, antithesis, and synthesis. What is thesis? So we who deal with natural science, this is true as well as in social science also, people who work in that particular area start with some hypothesis. And how these hypotheses are acquired? It is acquired from observation. And then let's say, what is the hypothesis? For one example, I throw an object, I see that, okay, the object falls down. So we take a hypothesis, general hypothesis, anything which has mass, if we throw upward direction, it will come downward. This is our hypothesis. Then we try to do antithesis. Antithesis means we try to do experiment. We try to contradict or negate the hypothesis with experiment. We observe for one object, we try to do it many objects, many different kind of object in a different way. We try to do the experiment and try to contradict the hypothesis. And if the hypothesis stand against many these contradiction, then we call it is synthesis. It is the law of nature. So this is the three-step general methodology. Is this three-step process. Of course, we can break it more further classification or further finer step, but this is the most basic steps. But we should remember that however obvious or impressive the laws may be, we cannot never claim to be this absolute. Law is supposed to change. If some new observation of new phenomena appears, then it might happen that our old profound law is not anymore applicable for this new phenomena. And we have to, being a scientist, we have to keep our mind open to accept that. And this is a one people call it a rational thinking process. So let us try to see one old profound worldview. One of
Dr. Banik?
Yes,
Yeah. Can you press hide on this pop-up window?
sure.
Yeah.
Yeah, is it
Thank
fine
you.
now? Yeah.
Yeah, it's fine. Thank
So
you.
let's consider a very simple idea. So let's say there is an opaque box, and in this opaque box there is some object. And we are interested in some properties of this object. Let's say we are interested in two properties. First one is this, we are interested in its shape, and it is promised that shape of the object is either circular or triangular. Means someone already keep the object either in circular shape or in triangular shape, but it is not told to us, and the box is opaque. And second property we are interested, it is color of the object. And again, let us assume that it is promised that color could be either red or it is blue. That is, these two property we are interested in. So there are four possibilities. So it could be a circular red object, it could be a circular blue object, or a triangular red object, or a triangular blue object. Now let us consider a measurement which will give us information about shape. So how to imagine such a measurement? So we can go into a dark room, we can put our hand inside the box, we can touch the objects, and by touching the object, we have an idea what is the shape of the object. But since there is no light, we cannot say what is its color. So we call it a shape measurement, the measurement which gives us information about shape. And from now on, I will denote this shape measurement, what I said in these things, by this diagrammatical box, that it has a measurement device. If we put the system into this device, it gives us information about the shape of the object, which could be either circular or it could be triangular. For instance, if I give this object, I will get this circular object, and that my idea is that okay, what is coming out of this measurement device, that is there is an object of circular shape. Now similarly, we can consider a color measurement. How to perform a color measurement? We can think, okay, make a very small pinhole. Now look through this small pinhole on this opaque box, and since it is a very small pinhole, it will only, we can see only part of this object. So we know the color of the object, but since we can only see the part of the object, we don't have the idea about the shape of the object. So it is color measurement. And similarly, we denote this color measurement by this green kind of object box, and it has input and output, and measurement outcome is red and blue. And if we give this object, it will give you, let's say in this case, it gives us blue color. Okay. So now, doing so, we can do this measurement, measurement of sequential concept. What does that mean? So let us, we perform this object, take this object and try to know its shape. And we obtain that its shape is circular. And then on the same object, I'm not changing the box, on the same object, I perform this color measurement. And we see, let's say it is blue color. Now we ask the question, again we perform the shape measurement of the same object, same box. We are not changing our box. So what result we should obtain? First, on the same object in a box, we perform shape measurement, we obtain circular outcome. And then we perform color measurement on the same object, we obtain blue color. Then on the same object, I perform the shape measurement. So what outcome we should obtain or expect? If we do this experiment, this is very common sense experiment. If we do this, we will obtain, of course, the shape is circular. So then what conclusion we can make? So we conclusion make, when the color was blue, at that time also the shape was blue. Shape was circular. So in other words, we can make a generic, very generic kind of conclusion. That means knowledge of color or one property does not destroy the knowledge of shape, means the other property. And now these properties could be anything. It could be mass, it could be height, it could be some other properties. So now we take it and we do this experiment many times, and from this doing this experiment many times, we take a general worldview stand. That means our shape, one measurement, knowing the one measurement does not destroy the property of the other properties. Or in other words, since it is not destroying, so when I measure this shape measurement, it was already shape, was circular. So my measurement just only reveal my shape, and that is true for also color also. So it was also already, it was in blue color. So my measurement just reveal the value blue color. So the worldview is that measurement does not create the value of the property. Rather, it reveals the value of the property. And this worldview is known by the name reality. So like as Professor Deshmukh was telling, that if we study a classical particle, let's say one-dimensional particle, single particle, so what is meant by reality of that particle? By reality, it means we assume that it has its position and momentum. And this is its state of the system. If we know the position and momentum of the system, then solving Newton equation, we can perfectly predict all its dynamical quantities. What will be its energy, momentum, angular momentum, everything we can predict. And moreover, the more fundamental thing is that even without don't observe the system is there with its position and momentum. This is property of the system. This is not my description about the system. That's why we call it reality of the system. So reality is something, some property which the system already possesses. Okay, so this is very old and profound idea of reality. So now in an early 20th century, some experiment was performed, that is this famous Stern-Gerlach experiment. Probably many of you already have studied this experiment. So what is this experimental details? Okay, so that is for the time being, it's not required for us, but you have to know that there is some microscopic particle was thrown through an inhomogeneous magnetic field. That is important part. Inhomogeneous magnetic field is required for this experiment. And let's say, since it is a magnetic field, we have to mention along which direction magnetic field is aligned. In this particular case, let's assume that, okay, magnetic field is aligning along Z direction. So when the microscopic object was thrown through this or passed through this inhomogeneous magnetic field aligned along Z direction, it was observed that, okay, some of the particle deflect upward direction and some of the downward direction. So why only two possibilities? Okay, that is using classical electrodynamics we cannot explain. So then we assume some concept of, okay, some intrinsic properties being that is required, but that description for the time being is not important for us in today's lecture. So it is happened, this observation or this experimental fact we are taking, we have observed this observation. And from now on, this I will just denote this whole measurement or setup by this simple cartoon box. So there is an oven, I perform this Z measurement. Z measurement means the particle is passed through inhomogeneous magnetic field aligned along Z axis, and there are two possible outcomes are possible. The particle get deflected along up direction or it get deflected along down direction. So, but there is no astonishing thing. I can think, okay, it is something like it was the shape of the object. I don't know earlier the shape. Now I perform the shape measurement, I get the knowledge of shape. Similarly, the particle was already what with some spin. I don't know, I don't have this idea. When I perform this measurement, one of the possible outcome come. So now let's try to put in an analogy, Stern-Gerlach setup and the shape color analogy. So if I do have shape measurement, there are two possible outcomes. Similarly, sigma Z measurement, there are two possible outcomes, up and down. So now I do this shape measurement, I obtain that shape is circular. On that, if I again perform shape measurement, I will again got the outcome circular. Similar things is happening here. I pass this particle in homogeneous magnetic field, and I am selecting only those particles who are deflected along upward direction, and then take this particle again, send them through this inhomogeneous magnetic field along Z direction, and I am obtaining only upward deflected particle, no downward deflected particle. So this is completely analogy in the shape measurement or our classical concept. Then we do this, first we do Z measurement and we select only the upward deflected particle and then do X measurement. What is mean by X measurement? This time we pass the particle through inhomogeneous magnetic field, but magnetic field is aligned along X direction. We are seeing that, okay, in this case, even we have selected only upward direction particle on the first measurement, when we pass through it X direction, both upward direction and downward direction are possible. So that is also, if you think, not too much astonishing. Okay, it is like as if we first perform Z measurement is like our shape measurement, we observe circular outcome, but okay, what is this color measurement? I am not sure. I have to do the measurement, and both red and blue color are possible outcome. So this is something like this is happening. But now we go a little bit further. We first perform Z, then X, and then again Z. So what is this shape color analogy? First I will perform shape measurement, let's obtain circular outcome, then perform color measurement, let's obtain blue color, and then perform shape measurement again. What I will obtain? I will certainly obtain circular outcome. But in this case, I already selected upward deflected particle on Z measurement, then I perform X measurement. Both are possible, up and down. I am just selecting up particle, and again I am doing Z measurement. And what I observe, both Z up and down are possible. In some case, up is coming, in some run down deflected particle we are seeing. So now, how to explain this phenomenon? This is our old stand worldview. What we take, that one measurement doesn't destroy the other measurement. That is now in a serious challenge. How to incorporate this experimental fact with this worldview? So our worldview was knowledge of color or one property does not destroy knowledge of other property. But in this case, knowledge of X actually destroying knowledge of Z. In other way, we can means when this theory, quantum theory was formulating by these big at that time Niels Bohr, Heisenberg, even Jordan, they say, okay, measurement in quantum world is very peculiar. Measurement not only create the property, measurement doesn't create the property, reveals the property, it actually creates the property. So the system doesn't possess its property. When we interact with the system, it creates its property. So now the question, the concept of reality was extremely challenged. So if reality was too much challenged, then what will be the problem? Because somebody we are trying to see, okay, means Einstein, why Einstein was so bothered about it at all, about this kind of concept. Okay, it is a peculiar kind of phenomena we observe in nature, and it is probabilistic, and probability, in many cases probability in statistical physics, it gives a very correct description. Quantum mechanics is giving correct description, but why Einstein was so much bothered about this kind of things? Because this is the philosophy part. Because you see, in scientific philosophy, it's called materialistic philosophy. Materialistic, and this opponent philosophy is in some sense it is called idealistic philosophy. So when quantum mechanics is was coming at that time, Bohr, Heisenberg, they are actually trying to take a position stand. They didn't take an explicit stand, but what they are trying to say, that is making an idealistic stand. That okay, reality doesn't exist. It is our consciousness as a who creates this reality. But Einstein was extremely against this. This reality, independent of us, it should exist. So now that's why there was a debate start between Einstein and Bohr. So it has actually a long history, and if any of you are interested, I can say one of the very famous book. This is by Max Jehmer, Philosophy of Quantum Mechanics. That history is very beautifully explained between these all debates. In different times, Einstein actually tried to come up with different argument, because he is not trying to accept He is not at a position to accept this quantum mechanics as it is. He is trying to come up with different argument to show fallacy of this quantum mechanics, and every time Bohr come up with some argument to give a counter argument that okay, your argument is not correct. So we know this kind of famous statement that Einstein used to tell that at any rate I convince that he does not throw dice. What does Einstein want to mean by this statement? He's trying to say this fundamental here by he or God, he means nature. That fundamentally nature should not be probabilistic. There should be a deterministic explanation underlying that. On the other hand, this Bohr response was Einstein stopped telling God what to do. That means, okay, how nature is, why are you dictating nature, what will be its description? Rather try to accept how nature it is. This is the main things. Now, as a physicist, our question is, okay, which stand or to whom we should support, Bohr or Einstein? Okay, so at that position, the debate actually was in a little bit philosophical. But in 1932, actually, historically, so that's why the Einstein was looking for some model or some explanation which will explain this underlying quantum nature, probability, and gives a deterministic explanation. But if we look back into history in 1932, von Neumann has actually a mathematical theorem that proves that such a hidden variable or deterministic explanation is not possible. Historically, in 1938, one lady scientist, physicist, Grit Harman, she actually come up with some argument that von Neumann actually takes some unnecessary assumption when he derived his mathematical theorem. But at that time, nobody cared about Grit Harman because, first of all, she is a lady mathematician and she is raising voice against the von Neumann. Means she was ignored. To be honest, she was ignored at that time. And then nearly 2 decades, there is not that much research in that direction. So we'll go to Bell's theorem, but for that, this is one idea of reality. We have in some sense understand that reality is the property of the system which already exists independent of our observed measurement or not, whether we study the system or not. So another concept we require. So now consider there are two parties, Alice and Bob, and they're space-like separated. And now let's say Alice is trying to measure some property of her system which she possesses. She may be interested into shape of the object as well as she might be interested into color of the object. Similarly, Bob might be interested into the shape of his object as well as Bob might be interested into the shape of color of his object. Now consider one instance, one particular case. Let's say Alice is interested trying to know the shape of this object. And this time Bob is also interested to know shape of his object. And let's say Alice obtain circular outcome and Bob also obtain circular outcome. Let us consider a different scenario. This time Alice is interested to know the shape of her object, but Bob this time interested to know color of his object. Now we can ask a question. Does it anyway matter whether Bob wants to know some property of her system? Does it matters whether Bob is doing what Bob is doing on his particle? Because Bob is in first separated. Let's say Bob is in alpha Centauri. For that, just to assume whether I want to measure shape of my object and I obtain outcome, should it depend what Bob is doing on his system? Because that should not depend. We take a stand. Why? That this should not depend, and we call it locality. Why? Because this is justified from relativity theory. Special relativity means this is we call relativistic causality. Means any cause-effect relation that has a finite speed limit, or no information can travel faster than light. So whatever Bob is doing, that requires some time to propagate at Alice end, but Bob is space-like separated. So what Alice will observe that should not depend what Bob is doing on her part, on his part. Bob might interested to perform shape measurement, or he might be interested to perform color measurement, but that should not determine what Alice will observe in her lab. So this is our locality assumption. But before that, you see, Einstein makes our physics local. Before that, physics was non-local. If you look into Newton's theory, if I move a mass here, immediately the effect, even if it is very tiny, it was throughout the universe. It was non-local, and not only non-local, you can actually send faster than signal using this kind of fact. And Newton was not happy. Means how to explain this phenomena, that I am doing something here and instantaneously that effect is throughout the universe. He was also not happy with this kind of this non-local behavior of his theory, gravitational theory. And that's why this Einstein theory is so revolutionary. He actually made theory local, and that is a revolutionary idea. So now Einstein, as I was telling, so this is our two very profound classical worldview. First one is reality, and the other one is locality. And in quantum foundation community, sometimes called it altogether as local realism or local causality. And if you are interested in more philosophy, so you can, this is a very good book by Reichenbach, Common Cross Principle. So any classical world, whatever correlation we observe, that can be explained within this local causal framework or local realistic framework. Now, as I said, Einstein was not happy with this quantum mechanical description. He is trying to come up with different argument, and every time Bohr gives a counter argument that there is some fallacy in your argument. Finally, in 1935, Einstein formulated a good argument. And what he is trying to say is that this is at that time some newspaper, Einstein Attacks Quantum Theory. Einstein means Einstein along with his two colleagues, Podolsky and Rosen, try to address some fallacy in quantum mechanics. Let me be more precise. What they are trying to say, that the title of the paper is, can quantum mechanical description of physical reality be considered complete? So now he understands finally, okay, quantum mechanics is not incorrect. It is a correct description, but it is not complete. Okay. Now let us try to little bit what EPR or Einstein, Podolsky, Rosen try to, what kind of question they are trying to pose. So this is already the Niels Bohr paper in reply to their paper that Professor Deshmukh was mentioning. So let's go to try to understand this EPR argument. But since all of you are already from physics background, this quantum mechanical description I don't have to repeat here. You already know a system is described by a state vector, which is a vector in Hilbert space. Probability is given by bond probability rule. The act of measurement, during the act of measurement, the wave function change suddenly or discontinuously, which is called collapse. It is not a unitary evolution. So in quantum mechanics, there are two kinds of evolution. One is this isolated system is evolved under unitary or Schrodinger evolution. Measurement is a different kind of things. It is a collapse, discrete jump. And finally, the composite system is described by tensor product system. If I have some, we have associated some HA Hilbert space for A system, HB Hilbert space for B system, the composite system is described by HA tensor HB. This is precisely a assumption, and many of these peculiar phenomena appears due to this composite structure. Even there are, in recent time, there are some debate is going on that due to this, even the black hole means black hole information paradox appearing due to this particular structure. But this is assumption, Copenhagen, because this assumption, this particular mathematical structure discuss many things. Means whatever this peculiarity at that time obtained, that cannot be explained within our classical language. If we take this axiomatic structure, all this we can explain. And probably this, if one has to, means too much serious about one of the postulate, that one is the last one, this tensor product postulate, because all this peculiarity arise due to this tensor product postulate. But this is not the all. There are a different way also we can do quantum mechanics. without assuming this. More general kind of formulation is possible, but that is not our aim to discuss today. So let us try to understand this EPR paradox, but I will not go to exact EPR paper. I'll try to discuss a variant which is described by David Bohm, because this is comparatively easier to understand. So what do you mean by completeness? This I am quoting from Einstein paper, EPR paper. They are trying to say every element of physical reality must have a counterpart in the physical theory. That means when I will say a theory is complete, you say if something is physical reality, then my theory should be able to explain this physical reality. If something is physically real or physical reality, that should have counterpart in my physical theory. This is their notion of completeness. Now we can ask, what do you mean by physical reality? Now you see, they say a sufficient condition. What they say? They say if without in any way disturbing a system, we can predict with certainty, that means with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Now you see, they are extremely smart. What is the definition of physical reality? They are not giving any definition, but they are trying to say, if without disturbing system, I can predict some property of the system deterministically, then that must be property of the system. It is not that my measurement or my interaction is creating that property, because I am not at all disturbing the system, but I am predicting the property perfectly or deterministically. So that is system property. You have to accept it. So that is their sufficient criterion of physical reality. And they say if such a physical reality is there, your theory should be able to explain that physical reality. Then we will call it as a complete theory. Now, how this EPR argument goes? Now, consider a source that creates a bipartite system, and one of the part is now with Alice and another part is with Bob, who are far separated. And according to Copenhagen or quantum means Copenhagen description, such a bipartite system, here we are assuming it is spin-half system, two spin-half system that can be prepared in such a peculiar state. So this is called singlet state. Many of you already probably know this state. So now, according to quantum postulate, if Alice perform measurement along sigma z direction, what is 0, 1? Okay, 0 is sigma z up eigenstate, 1 is sigma z down eigenstate. Now, if Alice perform sigma z measurement on her part, which result will come? So according to quantum mechanics, it is completely probabilistic. So 50% times Alice will get up and 50% times Alice will get down. But when Alice get up, immediately she can say, okay, you measure Bob system sigma z property, it must have been down, because the state immediately collapse. So Alice performs spin measurement along z. If her outcome is 0, she is certain that Bob outcome is 1. If her outcome is 1, she is certain that Bob outcome must be up, 0. Thus, without disturbing Bob's system, she can predict the value of z measurement of Bob. And why she is not disturbing? Because now Einstein bring the concept of locality. Einstein is saying, okay, if Alice is doing something on her particle, if some disturbance should go to Bob, it should take some time, because our physics is local. Any disturbance, anything should propagate with finite speed. But before that, Alice is already making that prediction and it is correct. We can write down this prediction and do this experiment, and every time you can see, according to your Copenhagen description, she is correct. So then sigma z must have a physical reality. Okay, so far there is no problem. One can say quantum mechanics there is a way to assign a physical reality to this sigma z measurement in quantum description. How to do that? You say prepare a state in sigma z eigenstate, then without disturbing the system you can predict its property. Because on eigenstate, if you perform the measurement according to Born rule, it will come with perfect 100% probability. So it is a physical reality is there. So now then they go on. They say this state is very peculiar. You can actually do the same argument not only for x, but even for not only for z, but now even for spin x measurement also. Because the singlet state take the same form the form of the singlet state looks similar if you write it in sigma x basis. Now sigma x plus minus is defined in this way. So now the same argument is true for sigma x measurement also. So now they say, okay, sigma x also has physical reality. Again, Copenhagen people say, okay, you prepare your system in sigma x eigenstate, then it has a physical reality. But Einstein will say, or EPR will say, no, our requirement of completeness not only sigma n and sigma x, both should have physical reality because both are physical real. Now then Copenhagen will say, no, that I cannot explain, because you cannot prepare a quantum system which is simultaneous eigenstate of sigma z or sigma x. Now this argument you can put for not only sigma z, sigma x, for any two non-commutating variable you can consider and put similar kind of argument. If we are in their paper, actually they have considered position and momentum observable because they are canonically non-commutative, canonical observable. So now what is the conclusion of EPR paper? So now their conclusion is, while we have thus shown that the wave function does not provide a complete description of physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. So immediately EPR paper, as I was saying, that EPR paper raised a huge debate among scientists. What should be the, okay, quantum mechanics is giving us correct description, but what should be the fundamental understanding of the theory? Immediately many people write paper. Bose take a paper, Bose write a paper, I think in next article, or it is 2000 this 35 in same year, same physical review journal. Bose write a paper in 1936. Schrodinger write paper and lots of paper. But all the discussion was, in some sense, was at philosophical level. Now the question is, which is correct? Who is correct? Einstein or Bose? Or in other words, a more fundamental question is how to explain nature. Because does such a model exist? So as I said, nearly 3 decades, there was not that much research in that direction. Only one exception was there. This is 1952 Bohm model. Bohm actually come up with a model description. What is deterministic? But this has something peculiarity in his model. It is some non-local phenomena, something is there. And this gives Einstein, John Bell, in some intuition. He says, he actually, who is John Bell? To be precise, John Bell actually by practice, he was a particle accelerator designer. Most of the time his life is spent in CERN, and then a few times in Bell Lab, and then come back to CERN. If I quote him, according to his language, I am a quantum engineer, but on Sunday I have principles. Means on my holidays, he used to think about these foundational questions. He actually looking for this Bohm, this von Neumann no-go proof, 1932 paper. But unfortunately, the book was written in German and he didn't know German. So finally, he requested some of his friends to translate it English. And then he was actually trying to understand this von Neumann argument and fallacy in von Neumann argument. And then he see this Bohm model also. And then it motivates something. Okay, let's try to see who is correct, Einstein or Bose. So that is his famous inequality. We will try to understand the inequality, but we will try to understand it by a very simple game. So let's try to understand the rule of this game. So there are 3 fellows, Charlie, Alice and Bob. And let's say Charlie is the referee. What is the rule? So Charlie asks question to Alice. And there are 2 possible questions Charlie can ask to Alice. The question will just denote it by 0 or 1. This is a notation. The 0th question or first question. 0th question or first question. And these are logical questions. Means Alice has to answer, for every question, Alice has to answer +1 or -1 outcome. Similar is for Bob. Charlie randomly asks some question y, which can be take 0 or 1 to Bob. And similarly, Bob has to give some answer +1 or -1. And another rule is there. Once the game start, Alice and Bob are not allowed to communicate with each other. So any possible kind of communication will be disallowed. All the phone will be taken away. Then you can say, okay, some electromagnetic wave can go. Okay, some electromagnetic shielding effect we will do. So all their possible way they can do, whatever physics they can use to communicate, everything will be blocked. So now, what is the winning condition? So let's consider one particular game. Referee say, okay, I will randomly ask you X or Y question. Many rounds you will play the game. You will give +1 or -1 outcome. Your condition, you will win the game if product of your outcome will be +1. Then you will win the game. So before the game start, Alice and Bob know, okay, we have to play this particular game. They can make some strategy, and now they are separated, spatially separated. Now the game start and no communication between them is allowed. The game start, many runs, the game will be played. So now we can ask this question. Can Alice and Bob win this game? Yeah, if we analyze a little bit, yes, it is possible. What? They have just decided, okay, we have to always satisfy this condition. Before the game start, they decided, whatever question Charlie asked me, Alice decided, I'll always answer plus. Bob also decided, whatever question Charlie asked me, I'll always answer plus. And you see, always their product is plus. So they win this game for all XY. Is this a strategy, only strategy? No, this need not to be only strategy. There could be other strategy also. Before the game start, they decided, okay, always Alice will answer minus, always Bob will answer minus. Again, their product will be plus. So again, this game can be perfectly win. Okay, let us try to make the game a little bit interesting. This time, Charlie say, okay, you will win the game if your product of your outcome is +1 when x is equal to y and -1 when x is equal to not y. But remember, Alice only know what question X is given to her. She doesn't know what question is given to Bob in a particular run. Similarly, Bob doesn't know what question X is given to Alice. So now, given this condition, can they win this game without communication? If we think a little bit, we'll find, yes, this game also can be win. How? So they have decided both Alice and Bob answer +1 when question 0 is asked and answer -1 when question 1 is asked. Let's see what happens. If we draw this table, you see Alice is asked 0th question, he answer +1. Bob is asked 0 question, he answer +1. So for 0, Alice answer plus. For 1, Alice answer minus. Similarly for 0, for Bob 0 0 he answer plus, and for 1 1 he answer minus. Now you see what is their product of this outcome. When x and y are same, that means 0 0 and 1 1 case their product is +1, and when their input is different, their product is -1. So it perfectly satisfies the winning condition of this game. So now this time Charlie make the rule a little bit more complex. This winning condition is this one. So ax times by should be -1 to the power xy for all xy belonging to 0 and 1. So now you can ask the question, can they win this game? No, this time answer is no. So how to prove that they cannot win this game? So what are the winning condition? Let us see the winning condition. So winning condition is this 4. A0 times B0 should be +1, A0 times B1 should be +1, A1 times B0 should be +1, and A1 times B1 should be -1. Look into if we take the value of x, y and put it here, this is the winning condition. Now can this 4 condition be satisfied always? No. Why? Because you just multiply, you assume there exists a solution for that. Yes, there is some strategy that can win this game. Now multiply this right hand side and left hand side. So left hand side, what we are getting? A0 square, A1 square, B0 square, B1 square. On the right hand side, what you are getting? -1. So right left hand side all are square quantity which can take value +1 or -1. So it must be a +1, and right hand side it is -1. So it is a contradiction. So this game cannot be win by 100%. Then what question we can ask? We can ask, okay, what is the maximum success probability they can win? So now that is also easy to argue in some sense. We can say Alice and Bob can decide, okay, always we will answer +1, whatever the question is. Now you see, always they can satisfy 3 conditions. So, and since all the question are asked with randomly, means with 1/4 probability, x, y are 4 possibilities are there. So out of 4, 3 conditions they can always satisfy. So 75% probability they can always win this game. Now it comes Bell. He proves that. Proof is again just I'm not given the proof here, but it can be shown that proof is just a one slide proof. If you assume your theory to be local and realistic, means your theory should satisfy locality as well as it should satisfy reality, then success probability of this game should not be more than 75%. It is always upper bounded by 75%. So this is this famous paper. The proof is very simple. It's just a 4 or 5 line proof argument. If you prove that, he proved that if you assume locality to be whole in nature and reality to be whole in nature, then you cannot have a success probability more than 75%. Now, if we let's try to do an experiment and see that, okay, we can win this particular game with more than 75% probability. So what is our conclusion? Our conclusion is then either some Alice and Bob is doing some cheating, some communication is going. Let's say in some sense we are capable to block that no communication is happening between Alice and Bob. And this is some kind of loophole in experiment. We have to be very careful. This is called locality loophole, that no such communication is happening between Alice and Bob. We can block this loophole. Then what is our conclusion? Then our conclusion is, in this experimental result, we cannot explain by a local realistic model. And Bell also show that in quantum mechanics, using the singlet state, the same state we discussed to this EPR paradox, we can actually have a success probability more than 75%, nearly 85%. It is not a fractional number, it is approximate number, I am saying. Actual probability is half times 1 plus 1 upon root 2. It's very close to 85%. So now Bell's theorem gives us a way to check whether quantum mechanical correlation we can explain by a local realistic model. Now we have to do this experiment. We are left with to just do this experiment. And this first experiment was actually, first experimental proposal was done by Closure, Horney, Shimoni and Holt, and some with Friedman. Closure actually performed some experiment also. Now we have to be very careful because it is, you see, our conclusion about nature, that whether nature can be explained by a local realistic phenomena. We have to, if any loophole is there, we are making a wrong prediction. So Closure gives them experimental path way to do that, but there was some loophole. Okay, now 3 different way loophole can come. First one is called detection loophole. So means these are this microscopic experiment. We have to prepare entangle photon, and then on polarization part we have to perform measurement. But since photon are very tiny, very sensitive, it might happen detector is not detecting this photon. So this is called efficiency loophole. Another is locality loophole. So photon is going, and after a certain time we are doing this measurement. Alice is doing this measurement. By that time already some information goes to Bob already. That we have to close. Means we have to very first change our measurement setup. This is called locality loophole. And there are other loophole also. This is called freedom of choice loophole. So now the question is, can we close all the loopholes simultaneously? That was the challenging part. So in aspect experiment, aspect closed this efficiency loophole and locality loophole. And then this is in 1982. And in 2014, there are 8 different groups who actually in different way perform this experiment, and all the possible loophole they close. Now it is conclusive, yes, quantum mechanics violates Bell inequality, and we can say furthermore, it might happen in some day next in coming future, we have to modify our quantum mechanics to address the question of quantum gravity. But whatever the new theory will come, that will also violate Bell inequality, because this is the experimental fact. This is the experimental fact. This is not about this artifact of our mathematics, Hilbert space artifact of quantum mechanics. Experimentally you obtain this violation. And finally, Jailinger, he has done a more sophisticated version of this Bell test. Actually, in this talk, I discussed two-party game, Alice Bob. We can actually discuss a three-party game, and where we can show an immediate contradiction. That is actually proposed by GHZ, Greenberger, Horne, and Jailinger. So GHZ argument. That argument that is also experimentally tested by Jailinger. So finally, this is their all paper, which is cited by Nobel Committee, and already Professor Deshmukh was mentioning that this is not only this foundation part, this Bell's theorem actually gives rise to lots of new applications, some of our communication complexity, quantum cryptography, device-independent randomness generation. Device-independent randomness or device-independent quantum cryptography means we'll say something based on the statistics only, input-output probability only. What is happening within the device, now the device is black box. How to describe this device? Is it quantum mechanics or is it some new theory? We don't know. We don't care about that. We just give some input into the device, take the output, and looking into that, we make some prediction. We can predict, yes, the statistics must be random. We can able to make a secure communication between or secure key between two distance parties. That is called device independent key distribution. And there are other many device independent protocols are possible, and still what other new kind of protocols are possible, that is not known. That's why this means in every few months new protocol people are trying to propose, and then trying to experimentally predict them, and then trying to other group trying to contradict their result, and the debate is going on, so that new discovery is possible. So in recent time, there are these are experimental papers, this random number certified by Bell's theorem. Then this satellite-based entanglement distribution, that means this entanglement, it is not established not only in lab, it is established in 1200 kilometers apart. One lab is in Vienna and another lab is in Beijing. One Vienna lab is Jailinger group and Beijing lab is Jailinger student. Now he is one of the forefather of Chinese quantum communication things, J.W. Pan. Between their lab, they have established entanglement, which is nearly 1200 kilometers away. And then they do it by satellite to ground quantum distribution, ground to satellite quantum teleportation, different experiment. And I was listening a talk by J.W. Pan. Their aim is to establish a quantum entanglement or quantum cryptography between the distance from Earth to Moon. But you can ask why they are doing all these kind of things. They are trying to say, yes, all depending on this noise, you can implement all this protocol. Now it's a question of technology which we can apply in our day-to-day life. So I'll end my talk with some few quotes. Alan Aspect, according to, in his view, Bell's theorem is nothing but a naive view of experimentalism, because he's talk about only statistics. This is the Henry P. Step. Professor Deshmukh was also mentioning that Bell's theorem is the most profound discovery of science. Of course, I may not 100% agree with Step, but it is one of the most profound discovery. There are other discovery even in last century, which is also similar or more profound than Bell's theorem, particularly in social science. So what Bell's view on Bohr and Einstein? So according to Bohr, you see what Bell says, Bohr was inconsistent, unclear, willfully obscure, and right. Einstein was consistent, clear, down to earth, and wrong. So what dream Einstein was seeing, the local realistic description, Our nature is not like that. We have to accept. Then you can say, okay, are we then taking a idealistic stand? No. We are again still in this, what is called? Materialistic stand. What Einstein was doing, Einstein was taking a mechanistic stand. Reality exists. How it exists? Okay, that is not a question of philosophy. That is a question of scientific category. The question of scientific category, Einstein uplifted to the question of philosophical category. How nature is, what should be the description of reality, that is a question of science. We have to keep open our mind, we have to do the experiment, and we have to take. Philosophical stand is reality exists, nature exists independent of us. How nature exists, that is a question of science. We will update our knowledge, we will interact with the nature, we will know, that we will go. And that's why I end the talk with one of my favorite quote by Marmin. What he says, what makes the pursuit of science so engrossing is to learn that one's most strongly held beliefs can be completely wrong. The search to identify and correct the old errors can lead to deep insight into nature. The world would be a far better place for all of us if this joy scientists find in exposing their own misconception were more common in other areas of human endeavor. With this, thank you for your patience. If you have some comment, questions, or discussion, I'll be happy to take it.
Thank you, Dr. Banik. Thank you, Dr. Banik, for the excellent talk. I mean, like, we got the more insightful information about the Bell's theorem. I mean, like, while Professor PCD was more provoked, he provoked us actually to think about what is the reality, and you try to complete the session that there are, what the Bell's theorem is all about. Yeah. So the session is open for the questions. If any of you wanted to ask the question. Yes.
Thanks for the talk.
Yeah, welcome.
So, how one can come up with, say, how one can attack to find one such inequality? Like, how do you attack that problem? Like, there are many such Bell inequalities.
How to come up with a new inequality? Is this your question? How to develop a new inequality?
Yeah.
Yeah. So, okay. So now you see, in this case, you look into the game. Alice is 2 input and 2 output. Bob has 2 input and 2 output. So what is the more general scenario? There are many particles. Alice, Bob, Alice 1, Alice 2, Alice 3, Alice 4, Alice 5, and so on. So now, there are n party. So each party has given some input, m input, and each input has some k output. So in that case, what will be the most general no signaling correlation? What do you mean by no signaling correlation? By no signaling correlation, I means any correlation that is compatible with relativistic causality principle. No means our theory, we don't want to be signal faster than light, instantaneous, or more profoundly, instantaneous signal we don't allow in our theory. So what will be the correlation description? That we can find. So it becomes a optimization problem, or means it becomes a polytope search problem. What will be the extreme point of this polytope? It is some convex set with finite number of extreme point. So how to find this finite number of extreme point? There is some already developed algorithm is there. So if you search, it's called this POTA, and there are different algorithms are there. But now the question comes, it is more difficult. Which correlation are quantum mechanically realizable? So what do you mean by quantum mechanically realizable? That means Alice and Bob share a quantum state, which is a Hilbert space vector, and then they perform some measurement, which is a Hermitian operator on their part, and then come up with a correlation. That is a much difficult question. And very recent result actually shows, if I understand correctly, the result, because result is not yet published, it is undergoing review, because it is a 200-page proof. That proves that this question is undecidable. That's why I'm trying to say that we have to be very, very careful to look into the assumption of tensor product structure. So now the question is something very common sense question we ask about the nature. Is this correlation available in nature? And the answer is no, we cannot tell that. It is undecidable. We don't know. There is no algorithm to find that. Undecidable means in computer science.
Okay, thanks.
Thank you, Dr. Banik. Anybody else? Anybody from the online participants? Nirmalaya? Professor PCB?
Yes, Manik,
Yes.
wonderful talk, as it was the last time I heard you as well. Excellent talk. So thank you very much for it. I have one small query.
Yes, please.
I am not even sure if it is a well formulated question, but let me ask anyway. There is this recent paper by Lee and Selby, which came a few years ago.
By whom?
Lee and Selby.
Okay. Okay.
Lee and Selby, and it is a no-go theorem, which raised the question that, okay, just as classical physics is an approximation to quantum physics in some sense, is there another theory? Is there a possibility of another theory which quantum mechanics is a good approximation and which will decohere into quantum theory? And the Lee and Selby, they argued in this that such a theory is not possible. It is a no-go theorem. Again, subject to some conditions. So I don't know what is the status of this issue. So
I particularly I don't know this work, but on the other hand, I know there are some results which actually say this is called almost quantum correlation, which is actually bigger than quantum.
I
So
see.
within quantum description, we cannot encapsulate them. So now you can say, okay, why we are bother about this kind of correlation? Because whatever natural principle we can thought about, this almost quantum set satisfies all of them. Like quantum mechanics satisfies all of them, this almost quantum is actually satisfy all of them. That rather it indicates other way around. It indicates we have to probably go beyond quantum mechanics. What will be the theory we don't know. But it indicates something bigger is something more generic kind of theory is required. That I can say. But of course I'll try to look into their paper. Because if is it John Shelby? John Shelby by one
I don't
researcher
know the
I know
full
John
name. I
Shelby is a
don't know
young
the
fellow
full.
I know.
Yeah, I have that paper on my laptop. I can email it to you.
Sure, it will be
I
nice.
will do that. Yeah.
Sure.
Thank you.
Yes,
Thank you very much.
Yeah, so Dr. Bobik, so I have a question like, for quantum communication, so do
Yes.
we need only that two-state system as qubit? Can multi-state system can be used?
Yes, multi-state system can be used and that will be more advantageous. In some cases, in some tasks, this means that's why now people are actually, I know some group in Australia, they have actually implemented optical system, but not only 2 degrees of freedom, polarization are 2 degrees of freedom, but two-dimensional Hilbert space, you can say, C2 system. But they are trying to use the more dimensional Hilbert space for communication perspective, because that will be more advantageous. Now in technically they call it, I don't know, it's called special mode of this photon. They are trying to use that for communication perspective. Mathematically, what does means? It's a higher dimensional Hilbert space they are trying to use.
Okay, but this the currently what are the algorithm is there? Is it kind of partially kind of mix of classical and quantum?
Algorithm by algorithm, what do you mean? Means like
Means
this
that
Gomar, Shor, this kind of things?
Yes. So what you said now that the actual communication is possible, that then you have to make
No,
a
those
different
are
algorithm to detect.
no. This quantum communication part, what is established, is what I am trying to say. This 1200 km apart distance, that is fully quantum. That is there. That is fully quantum mechanical communication.
Okay.
But algorithm part is different. That is this computational part. That is not yet. We don't understand when will quantum computer come, and actually there are lots of skepticism is there when we will get this quantum computer, or at all we will get or not. The hype what is created, that is in some sense industrial hype. But in true academic sense, what will be the future of quantum computer, that is not well known answer. I think not only me, all the big shot also cannot give to all. This is just a industrial hype. But communication is a reality. Communication, random number, those are reality. Quantum computation in some sense, little bit hyped is there. So we have to be very careful when we make this comment or this kind of things. Every 15 days, 7 days, we see some result. Okay, that supremacy has been achieved, and by next 7 days, another group say it is not a valid comment, unnecessary demand. So academic perspective, we have to be very careful.
Any other question from online? Yeah, you have another one? Okay.
So I have one more question.
Sure.
When Alice and Bob communicate, you said that they will be initially sharing the key via classical process, like this. They make a phone call or something like that.
Yes.
And then they send the qubits or something, like some state. Right, like when they share the key by classical communication.
Yes.
So don't you think like there can be a spy who can read the key actually is?
Exactly. That's why we are moving to. People are trying to move to quantum cryptography, because let's say you and me want to make a secure key. So what you will call me? Okay, somebody is tapping this phone line. You will hear what we are discussing. That's why we will try to make a quantum communication line where if you disturb something, because if you disturb particle, if you try to encode your message in sigma z or sigma x randomly, if it do something on this part, it will destroy the state. So immediately by doing performance, I will know whether eavesdropper is in between there or not. So to be honest, to be more precise, in classical world, the cryptography or security is given by computational complexity. So it is secure up to the constant that a problem is mathematically tough. But in quantum world, people try to devise a security which is law-based security. Means if you believe that instantaneous signaling is not possible, then your key is secure. So now there are different protocols. The first was actually the first quantum cryptography protocol which was discovered, that was published in a India conference, Bangalore conference. This is the famous BB84 protocol, Bennett and Russert protocol. This was first announced or discussed in a conference, IEEE conference in Bangalore. Then there are lots of different protocols out there. Eckhart protocol, Eckhart 91, then BBM, Bennett Russert, Marmin 92. Lots of, if you are interested, you can find. Still people are trying to come more practical, try to make this protocol more practical and experimentally feasible, more this kind of questions.
Okay. What do you mean by quantum channel? I mean,
by quantum channel means quantum communication line. Classical channel means which can send you a classical bit up, down. Quantum channel means it can send you a quantum qubit.
Okay.
Yeah, it can send the keeping the coherence intact.
Okay, thanks.
So let's thank Dr. Banik one more time for the excellent talk. With that, actually, we come to the conclusion of this 2 hours event on the quantum entanglement. I request Professor Suman Kalyanpal to conclude the session with his remarks.
I don't know why Dr. Sunny told me to conclude, but he was really handling the program. So, but at all, being a chair of the school, I'd like to thank Professor Deshmukh for finding his time from his busy schedule, and it's really nice that this presentation. So we help us at least to think more basic questions from the quantum mechanics and then original questions, I can say. And of course, I hope that students also get already got some thing to think for future. Okay, and I hope that it would be good that we can get you here, but at least COVID learned us that even we don't need to be local, we can be non-local and we can hold this kind of event. Okay, so but anyway, so we would like to have you in future here. Okay, so I would be happy to host you sometime in future. And also, I'd like to thank Dr. Banik that it was also a nice talk, and it's a kind of complementary, the two talks, and so that our team has nicely organized together. So thank you, Dr. Banik. So I hope also that we will be happy to host you here sometime in future. And then of course that in future that if we need any help from you, any purpose, so we will come to you. I hope that we'll get your help. Okay. So thank you all again. Yeah.
Thank you.
Okay, thank you everybody.
Thank you very much, Dr. Banik and Professor PCT. Thank you very much for your time.
Bye.
And thank you, Nirmala and Ajay, for organizing these talks. Good.